So I'm going to record the solutions as I'm writing them, so you can either watch the video or look at the Word file. Okay, let's see. First of all, this thing is working, right? Good. Okay. So the first thing is the cute robots question. So the important thing so basically we already established that he has low battery, so he needs, like, essentially he can't walk too much. You have to assume first of all that the power consumption for robots is mostly for the physical activity and not for the computation. Okay, so it doesn't want to walk too long, so it needs optimal solution, and it has not enough memory, so it needs a blind search which has optimal solution. Okay, so need blind search which is guaranteed optimal, right? That's why you go with IDDFS, because that's the only blind search that is guaranteed optimal. Okay, so DFS won't work. DFS won't work because it basically is not optimal, and so that means if it has to walk longer, the battery gets over. Okay, and similarly a star search won't work because I'm asking specifically which blind search method can it use. Okay, fine. Let's just use a different color. Okay, so that's for the first question. Okay, if you said DFS, you got partial credit, but obviously IDDFS is the only correct answer, really. Okay, the next thing is in fact, the B part depends very much on the answer to the A part, because C3PO is still doing blind search, and now it says it's quite certain that the goal is at least K moves away. Notice that it is at least K moves away. Okay, not at most. Many of you looked at it as at most. At most would basically give you a depth limit. At least will give you the limit at the minimum depth after which the goal can exist. And in fact, pretty much the only search strategy that can use this information turns out to be IDDFS, because IDDFS can skip the first K iterations. First K iterations and then start. Okay, so that's the basic point. Okay, now the next thing is, would it make sense for C3PO to use a star search with heuristic value set uniformly to 0? If you set it uniformly to 0, you are getting breadth first search. Okay, breadth first search essentially, which has B power D memory, and so not only is it blind, but it also is taking too much memory, so won't work. Okay, so that's the basic point for that. Now for the last one, we are talking about mod x plus mod y, absolute values. That's essentially Manhattan distance, and Manhattan distance won't be admissible because you can make diagonal moves. So for example, suppose this is 0 0, and suppose you are somewhere here 5 5, then the shortest possible distance is 5 moves, 5 diagonal moves, but this guy will say 5 plus 5 10 moves, and that is not valid because it's actually overestimating, so it overestimates, so inadmissible. Okay, so that's the answer expected there. So now going to this problem. So for this problem essentially, you're doing a star search. Okay, the thing to remember is you start with the open list, with just A in it, and then so you take out expand A. Okay, you get B and C. Now B will have G value of 8 plus H value of 4, so 12, and C will have G value of 14 plus H value of 0 or 14. So now you take B, expand B, you will get D and E. So now so expand B, you'll get D and E. So D will have the G value of 8 plus 3 11, 8 plus 3 11, plus H value of 2, which is 13, and C, who's been standing around, will now be actually still 14, so it's going to be behind it. And E has a G value, E has a G value of 8 plus 14, 22, plus H value of 0, so its F value is 22. Okay, so then what do? We essentially have to take, I go back. So, 1 second. Yeah, so we essentially will take D, expand D. So this is expansion 1, this is expansion 2, then you expand D because that has 13, which is the lowest F value. So at this point, when you expand D, you'll just get F. Notice it's a directed graph, so you'll only get F. And the F's G value would be G value of 11, which is 11. So G value of D, which is 11, plus 7, 18. Okay, and F value, H value is 0. So you have, so you have your Q. Now C comes to the front, 14 plus 0. F will have 18 plus 0. And E will still have 22 plus 0. Okay, so we are actually full of goal nodes, except the node that you pick will be the first one, the C. And then you expand C. When you are expanding C, you realize before you expanding, you see it's a goal node. So stop. Okay, so there are 4 expansions. A, B, D, C are the expansions. Okay, so that's the answer to that question. Now to go to this, what I'll do is I'll take, I wish I could take this, let's see if I can copy this. Yeah, actually it's not possible. Okay, so we'll just do this. I'll first put this. Okay, I can put this, I guess. Put this and then select this and put it up so that it will be easier for me to explain what's going on. Okay, so in this case, when you're doing IDA star, right, when you're doing IDA star, the very first iteration, you have just one little tree A, and you start expanding this tree basically, and then you will realize that the F value for B is 12 and F value for C is 14. So you just, the lowest F value you saw above cutoff, basically, currently we don't even define cutoff for the first iteration, but essentially, the lowest cutoff is B. So the new tree that you will be doing is A, B. Okay, B is 12 F cutoff. Okay, so then so in this case, you expanded A once already. and here you are again doing depth first search. So you expand A and you expand B. Okay, so when you expand A, you get C back again, which is 14, and when you expand B, you will get D, which is 11. 8 plus 3, 11 plus 2, 13. Okay, so the F cutoff is 12, and D is the first node that is crossing it. So you essentially will include D in the next iteration. So the next tree you will be looking at is A, B, D. Okay, and then again depth first search will do A expansion, B expansion. When it does A expansion, it will get C with 14. When it does B expansion, basically it will get E. Actually, yeah, it'll get E with 12. So it'll get E with 8 plus 14, 22. So D is still with 13, of course. Okay, and by the way, here when you did expansion of B, you also must have considered E, which is 22. So we didn't care about it because it was all of these, this and this are crossing the cutoff, and so you take the lowest one and include it into the tree. Okay, so the only way more than one node can enter the next iteration is if all of them have the equal F value and the minimum F value. They all have the minimum F value which is above the cutoff. So in this case, you only included just one node at a time. Anyway, so at this point when you came back here, you have a C14, which will be the highest, the lowest value that still is above the cutoff 13. So by the way, here the cutoff is here the cutoff is 12. So here is the cutoff is 12, and here the cutoff is 13, and then next one will be cutoff will be 14. So when you get cutoff 14, you will get A, B, D, C. Okay, in this case, once again, when you are expanding, B will bring in E with 22, and D will be anyway 13. But then you will expand A, then you expand B, then you expand D, then you will expand C, and then this time C is the goal node, so you stop. Okay, so the number of expansions are 1, 2, 3, 4, 5, and then of course D here 6. By the way, when you expand D here, you did consider F also, and F would have been 11, 8 plus 3, 11 plus 7, 18. Okay, that's why it didn't really make a difference. Okay, so once again, you would have considered this A, B, C, A, B, D, C, and you will end with C. Okay, so IDA star will essentially do these many expansions: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 expansions. Okay, that's for that problem. Now, what's the largest possible value the heuristic value of B can take without the heuristic being inadmissible? That's the idea there basically is, if you look at the picture, so you're talking about what is the largest possible value of B, the heuristic value of B, such that it will still be admissible. To do that, you have to consider what is the true shortest distance for B to a goal node. B can reach a goal node here in 14 units. It can reach a goal node here in 9 units. Those are the two goal nodes. I'm sorry, in 10 units, 7 plus 3, 10 units. Those are the only two goal nodes it can reach. And so really the shortest goal node it can reach is 7 plus 3, 10. So its heuristic value cannot be more than 10. Okay, so 7 plus 3, 10, that's the closest goal. So it needs, so the highest, so the shortest goal node, shortest or the closest goal is 10 units away. from B. So h of B must be less than or equal to 10. So highest value is equal to 10. Okay. Some of you decided, somehow E is closer because it's only one step away. But what matters for A star is not how many steps away, but what is the cost away. And here it's 2 steps away, but it's only 10 units away. Here this is 1 step away, only 14 units away. Okay, so HB. Now, the next question is, if in fact HB becomes 10, if this HB becomes 10, right, then is it monotonic? Now, for it to be monotonic, you just need to check. I mean, basically, to check it's monotonic, you have to show that everywhere f of a node is is not lower than f of its parent. Okay, but to show that it's not monotonic, all you need to do is show one pair of parent-child nodes such that f value of the child is actually lower than the f value of parent. Okay, so now if you take f of b would be g of b, which is, what is g of b? G of b is 8 plus h of b is 10. So 8 plus 10 will be 18. Now if you take f of d, everything else remains the same. So f of d will be 11 plus 2, which will be 13. So that means, in essence, you're saying f of b is higher than f of d. And so in fact, f value did not increase, it actually reduced. Okay, so heuristic is not monotonic. Okay, actually one of you have done path max correction. Now after you do path max correction to heuristic, it will always become monotonic. Okay, but I was asking whether it is monotonic or not to begin with, and it is not. Okay, and once again, the reason you do path max correction is this makes no sense. Essentially, this says the shortest path that starts from the root node and goes through B to a goal node is 18 units long. And this one says the shortest path that starts from the root node, goes through B and goes through D is only 13 units long. How can that reduce? It makes no sense. Okay, and that's because basically the heuristic is not consistent. It's not, so f value is not monotonic. Okay, so that's in fact this one is a more involved answer than this one. So anybody who got it right, a few of you got it right, you got extra points for that. I think I gave 4 instead of 2 there. Okay, so that's basically the, with that, now for the counting of the states, what is the size of the state space? If you have 5 Boolean state variables, of course 2 power 5. If you have regression, basically because a state will have in each state, each variable can either be true or false. So 2 times 2 times 2 times 2 times 2 equal to 2 power 5. Now in the case of regression, you are considering partial states. So basically a state may either have the variable true, variable false, or variable not present. So each variable can have 3 possibilities. So 3 times 3 times 3 times 3 times 3 equal to 3 power 5. Okay. Now if the agent now loses its perception and doesn't know which state it's currently in, what is the size of the space it needs to search? That's basically, we talked about this. Essentially, it has to search in the space of belief states, and belief states, a belief state is a set of states. Okay, a set of states. That means you need to consider, each subset of the original states can be a separate belief state. And if you have, if you have n items, you can get 2 power n subsets over those items. And if, in our case, you have 2 power 5 states, so you can get 2 power 5 belief states. Okay, so that's the price you pay for losing your eyesight. Now, when you miraculously get partial perception, you know that if you have complete perception, you are searching in a 2 power 5 space. If you lose all perception, you are searching in a space of 2 power 5. And so basically, and so now how much is the space for the partial perception depends on how much perception you have lost. The best you can do is you can be anywhere between 2 power 5 to 2 power 5. And in fact, I think one of you have given a very nice answer. So for example, you pointed out that if you lose the ability to, if you get the ability to evaluate two of the variables, that means you know those variables, okay, then in essence you still don't know three variables, what their values are, so it would be 2 power 3, okay. And then basically that's how I'm sorry, not, let's see, we get the ability to evaluate, you know that if you get the ability to evaluate all 5 variables, then in essence you get 2 power 5. If you do not have the ability to sense any of the variables, you're searching here, and the more variables you can sense, the smaller your search space is. And actually I'll send you a mail later on, but essentially the space you search would be related to the number of variables you can sense. Since I'm recording this, I'm actually not going to cut this. I'll come back to this later. Okay. Next. So then this one, the progression, it's quite simple, obviously. So you start with initial state J, and then you can apply O1. If you apply O1, there are no preconditions, and it makes P true and makes J false. And so that means essentially only P holds, and you actually have not J, but you don't write negative values, because by convention you assume you only mention the true variables, and the false variables, every other variable is assumed to be false. So when your state is P, that essentially means that P is true and Q false, J false, and in all other variables are false, so Q and J are false. Okay. And then the other side, if you apply O2 requires J and gives Q. Okay. Now the interesting thing is, remember that it gives Q and you copy the rest of the state. So J will also have to be copied. Some of you did not, and that's a mistake, because essentially you must say all the variables that are actually positive, okay, that are all true. Okay. So, and then this is the first level. Now of these, if you actually go forward on this and you apply, so if you do this P, okay, so you need Q. So if you cannot apply so O2 QJ. Okay, let's see, something I'm doing wrong. So P is true, J is false, that's fine. And then O2, Q is true, J is false. Yeah, and then so if from here, if you apply O1, from here, you would get because O1 doesn't require any preconditions and gives P and removes J, so you'll get Q and P, and that is your goal state, so you're done. Okay, that's basically a path to the goal. Now doing the regression, if you're doing the regression, once again, let's see, okay, yeah, if you're doing the regression, you start from the goal state P, Q, and then you can have O1 as the last or O2 as the last. Now, is it possible to have O1 as the last? Well, it is if in fact its effects are not inconsistent with what you have here, and in fact P is consistent with P and it doesn't say anything about Q, so O1 is fine. And if O1 is there, then you no longer need P, so you need to still work on Q, and that's it, because O1 doesn't require any preconditions. So the state here is just Q. That means you want to make sure Q is true, that's all. Some of you wrote J, etc. here. That doesn't make any sense. Only Q needs to be true before O1, so that after O1, PQ will be true. And similarly for O2, again, the effects of O2 are Q. That Q is consistent with the goal state, and so you can write O2. So since Q is already taken care of, P will come back here, and then unlike O1, O2 has a precondition J, so you have to write the precondition J. So that's your goal state. That's your state here. Okay. Now, of these, it turns out that if you were to apply O2 here, okay, then O2 gives Q and requires J, and so all you need is J before, and that J is true in the initial state, so in some sense it's grounded now, and so the plan is that. Okay, so this part is planned. So O2, O1 is the plan. Interestingly, in fact, as one of you have pointed out, interestingly, although you didn't need to show it, but one of you did show it, Pj, this state actually doesn't go anywhere. It's actually dead, because in this domain you cannot actually reach any state where P and J are true together, because the only way of getting P also deletes J. Okay, and so Pj can never be true together. Okay, so in fact that's something that somebody pointed out that's kind of nice in this case. Okay, so that's about regression. Again, this is the correct state descriptions. I cut off points if you either, in some cases here, for example, here, some people put not J, and some people here did not put J, but you have to follow the convention. Every positive literal has to be shown, and if it's not in the forward search, if something is not listed as positive, then it's assumed to be negative. On the other hand, in the reverse search, you need to show everything, because in some sense it's a regression state. Okay, and it's a partial state. So if it's not present, normally you only assume that you don't care about it. Okay, by the way, so that's something that's important thing that I mentioned. I may not have, it doesn't make a difference in this case, but if your actions have, so this is like a digression, if your actions have negative preconditions, then regression states will have negative literals. You have to mention them, because unlike progression where it's a complete state, in regression it's a partial state. So if you don't mention if you don't mention something, it means you don't care about what its value is. It doesn't matter that it's true or false. So if on the other hand, if you regressed over an action which winds up having, let's say, a negative J as its precondition, you better ensure that you work on making not J true. Okay, and that is something that I didn't go into detail in the class, but really there's nothing particularly positive about positive versus negative, right? You could sometimes have goals which are negative. So for example, don't destroy the world is a good goal. Okay, so it's a negative goal, but it's a good goal. And so when you're going backward, then you essentially want to make sure that that's, your regression states can have negative goals. But this is a digression, it didn't matter for this particular problem. Okay, finally we are, and so I have spent 30 minutes already, So finally, we are in these short answer questions. In this case, there are many ways of doing this. One example, of course, is get dynamic, because everybody needs to be dynamic. So dynamic, let's say there's a kid in the room, and then assuming vacuuming scenario, and to get deterministic, non-deterministic, have good versus faulty motor. Okay, that, and then accessible, inaccessible, you have good versus bad sensors. That's all. Okay. Now this next one, the pattern database thing, actually a lot of people, in fact only one person got it right. The point about the suggested way in which a pattern database heuristic can be guaranteed to be a perfect heuristic, then the idea is that, notice that if you have you essentially considered subparts of the puzzle as the pattern, right? As long as you only have subparts of the puzzle as the pattern, they are not necessarily perfect. Okay, so to make it perfect, you consider the entire puzzle as the pattern. Okay, so the pattern should be the entire puzzle, in which case then it will be perfect. So consider the entire puzzle state as pattern. That means everybody should be in their right place. Whereas if you consider this, that means you only considered these guys to be in the right place, and you more or less ignored all other tiles. Saying, for example, that pattern database should have every state and its heuristic value is not sufficient, because every pattern database has every state's heuristic value. It's just that many states have the same heuristic value. Here, every state might have very different heuristic values. Okay, so that's the one for the pattern database. This is mentioned. If you go back to the pattern database lecture, it was mentioned explicitly in the class. In fact, there's very little I asked on this exam that I did not explicitly mention in the class. And finally, give a reason why progression search might do better than regression search. Progression search searches in 2 power n space. Regression search searches in 3 power n space. So advantage progression. Okay. On the other hand, regression search, regression could be better because regression search is goal directed. Goal directed has low branching factor, because there are fewer things that are relevant to what you want to achieve than are things that you can do in any realistic world. Okay, those are the two usual explanations. Okay. Now this one is interesting. So you're talking about a big tree which is totally of depth d, and then the goal is at a depth small d. Okay, now if you're doing IDDFS, obviously you'll come all the way up to this part, and so you'll first, next, and so on. So the root node would be expanded basically d plus 1 times. So order d times. Okay, if you're doing IDA star, essentially every iteration one extra node can come. So it's essentially there's be exponential number of nodes. Okay, now the question is, what is the really worst case? I basically gave so the really worst case is you have to go through the entire space, this whole space, and then find this is the best node. And so in some sense, the number of iterations is order of b power d. Although I did give full points if you just said b power small d as the number of iterations. Okay, and finally this one is a direct homework problem, right? If you have h that is not admissible but overestimates by k units, then obviously the solution can only be at most, the solution found by A star search can only be at most k units away from optimum. Okay, and so that's something that we can prove, and essentially you actually proved it, and so the solution would be at most k units away from optimum. Okay, that's it. That's all the solutions. So I'm just going to put this up. I'm going to stop this.